All right, so we're starting with page, it looks like it's 112, number 17. Okay, so this is a bit of reading to do. So it says we have this function and a t is equal to 20 minus 30 over the square root of 9 plus t squared. All right, and this tells us that it represents the number of items that cashier can scan per minute with respect to time and hours. Okay, so this tells us how many items per hour they can scan per minute relative to the number of hours that they're working. And they want us to first find n prime at t, the rate at which the cashier's productivity is changing. Okay, so notice that this gives us the rate in terms of items per minute. Okay, depending on how many hours they work. So maybe that goes up or go down depending on how many hours they work. And we want to know how that productivity is changing over time. So let's find the derivative of this here. Okay, so derivative of 20 is just a constant. Okay, just a constant, so it's going to be equal to 0. Now here, I could use the quotient rule, but instead, the way I'm going to find this derivative, so notice here I write the derivative with respect to t, because that happens to be the variable in this particular instant. So I'm going to rewrite this as negative 30. So I'm assuming I've already taken the derivative of 20, which is 0, and I'm going to write this as 9 plus t squared to the negative 1/2. Okay, so instead of using the quotient rule, I'm going to rewrite it as a power, given that the negative 30 here is just a constant. Okay, any issues with this? Okay, so now I can use the chain rule. Okay, well, I'm first using the constant multiple rule, so I've got the negative 30, and now let me open a big bracket to use the chain rule here. So we've got the outside function is u to the negative 1/2, so that's negative 1/2 times u, which is 9 plus t squared to the, and here negative 1/2 minus 1 is going to be negative 3/2 or negative 1.5. And then I'm going to multiply that by the derivative of u with respect to t, which is just going to be 2t. Okay, so there's my derivative. And because it looks like I'm going to want to work with this equation in b, I'm going to do some simplifying. Okay, so here we've got the 2's, one in the numerator, one in the denominator, that cancels. Okay, and let's see what we have. So this whole thing is going to go into the denominator. So the only thing left in the numerator is this 30, which is going to become positive because I'm multiplying those two negatives. So it looks like it's 30. And then here in the denominator, we have 9 plus t squared all to the 3/2. Okay, because now this negative exponent going into the denominator becomes positive. All right. So this is my derivative, and now let's take a look at what they're asking in B. It says, according to this model, does the cashier ever stop improving and why? So does anybody want to tell me, based on what we have here, why we can say that the cashier is always improving? What's the particular characteristic that this derivative has that we can make that
E has to always be greater than 0 because it's squared. It can't be a negative number.
Yeah, so here we look at the denominator and you have 9 plus t squared can be at most 0, or sorry, it's going to be at least 0. So this is going to be positive. We see that the numerator is always positive since it's just 30. So here, because n prime at t is always greater than 0, okay, we know that the rate of change is always positive. Is always positive. Okay, and of course in this case here, okay, what does a bigger n represent if it's increasing? Well, it means scanning more items per minute. Okay, so here the rate of change is positive, therefore, okay, rate of scanning always increasing. Now, how, just to add a bit of just add a little bit of context here. Does it make sense that this would be true for all of eternity, essentially for t greater than 0? Probably not. So probably, this equation and this research that they're doing is probably for a reasonable amount of time. So maybe somebody working for 6 hours or 8 hours, presumably after 24 hours, their rate of scanning would go way down because they'd hardly be able to stay asleep. So just want to keep in mind that anytime we have these models, they're likely only useful for a certain amount of time. Okay, any questions on this here? And it could be, I'm wondering if the issue was I think the textbook, at least the one I had, has 1/2 in the denominator. And it doesn't change our answer to part B, but maybe that first part. Okay, any questions on this or move on? Okay, let's move on. All right, next one I have is page 263, number 8. Okay. All right, let's see what this says here. It says, determine the equation of the tangent to the curve defined by, so let's write our function, x minus e to the negative x. Let me just check that that's correct. Yeah, it looks good. Okay. Okay, and it has to be parallel to the line represented by 3x minus y minus 9 equals 0. Okay. So first thing, I want to make sure I know what I'm looking for. I'm not just looking for a slope. I'm looking for the equation of the tangent line. And we have to keep in mind that when I'm looking for the equation of the line, I need two things. I need a slope and I need a point. Can anybody here tell me how I can find one of those things really easily based on the information that they're giving me? So this tangent, it's to this curve, and it has to be parallel to this line. So who can tell me what one fairly easy piece of information is going to be?
The slope is given because there's already the 3x minus y minus 9 thing. And then if you just rearrange the y, it becomes evident that the slope is 3.
Yeah, so here we just rearrange this here and we get 3x minus 9. So since it's parallel to this line, I know that the slope of the tangent has to be the same as this one here. Okay, so I've got the slope. What I don't know is the point at which. Okay, so this is where I know that whatever rate of change I'm looking for, it's got to be equal to 3. And then hopefully I can determine what x value that's going to occur at. And of course, what's another possibility? Okay, there's no guarantee that there's only one answer. Maybe there's two tangent lines that have a slope of 3. So it would depend on the shape of this function. Okay, but we don't have to worry about that because the algebra is going to do the work for us. So let's excuse me. Let's take the derivative here. So derivative of x is just 1 minus, and now here I'm going to have to use the chain rule. So my negative x is going to be my u. So derivative of e to the u is just e to the u. And then I have to take the derivative of u, which is negative x with respect to x. So that's just negative 1. Okay. So I have seen people recently forgetting to take that derivative of the negative x or the negative 2x. Make sure you're taking that. So in the end, this derivative is just going to be 1 plus e to the negative x. And we need this to be equal to 3. Okay, and now this is an equation that we should be able to solve because we can easily get a single exponential expression equal to a number. Okay, and so this is where we take a logarithm on both sides. I'm going to take the natural log of both sides. So we have ln of 2 is just going to be equal to negative x. So x is equal to negative ln 2. Okay, so this is the x component of the point where this curve has a rate of change of 3. Okay, but of course, something else I need. what else am I going to need in order to complete this thing here? What's the last piece of information I'm going to need? Who can tell me that?
The y value.
There you go. And where am I getting the y value from?
You input the x into the original equation.
Yeah, of the curve. Okay, so sometimes the mistake is, oh, let me just input it into this linear function. Well, no. This is just this linear function is just parallel to the slope of the tangent. You know, there's no indication that this is the actual tangent line. So now I'm going to put, take this y and input negative ln2. And what do we get? We get negative ln2 minus e to the negative of negative ln2, which of course those are going to just reduce to positive 1. And so here, what do we have? We have e to the natural logarithm of e, base e of 2. So that's just going to be negative ln2 minus 2. Okay. So now that I have a slope, I have an x value and a y value, I can now find the equation. And it's in these types of questions, similar to the one we also saw in the quiz, where point slope form is so much easier, because here it's just y minus the y value, negative ln2 minus 2, equals the slope, which is 3, times x minus the x value, negative ln2. And now I can just clean this up. I'll solve for y. So this whole thing that's being subtracted is going to go to the other side. So 3 times, this is just going to be x plus ln2. And then this is just going to be plus, negative ln2 minus 2. Okay. And if I wanted to, I can just keep distributing and simplifying, but I'll just leave it like that. Okay. So in the end, the only really big difference in this question compared to other questions we've done is that we're having to work with these, slightly unsavory numbers that we would prefer not to have to work with. But, in the end, they're just numbers. All right. Any questions on this? I'm not sure who asked this one. No. Okay. So let's take a look here at, so I think the next one is going to be 6B on 575. Okay, so 6B on 575. Let's see if we have enough room here. Okay, so this says for each of the following functions, solve the equation f prime at x is equal to 0. And this was, what was it? B. So it's ln x plus 2x. And it is all to the 1/3. All right. So obviously, first thing I'm going to do is take the derivative. So f prime at x. So here I'm going to be using the chain rule. This whole thing inside the bracket is my inside function. So first I'm taking the derivative of u to the 1/3. So that's going to be 1/3 u, which is this whole thing, to the negative 2/3. Okay, and then I'm going to multiply that. The second link in my chain is the derivative of this inside function. And this derivative of ln x is just 1/x. And then here plus the derivative of 2x, which is just 2. Okay. So there's my derivative. I know I want my derivative to be equal to 0. So let me start cleaning this up a bit. So the only thing I'm left in the numerator with is just the 1/x plus 2. This 3 is in the denominator, and this whole expression is going to go into the denominator as a power, 2x, a power of positive 2/3. Okay. Now, what's nice about this question is this whole thing that's in the denominator is actually of no consequence to me. Well, it's not completely of no consequence. I need to make sure that whatever answer I get doesn't make the denominator 0. But we know that in order for a fraction to be 0, the numerator has to be equal to 0. Okay. Now, this is technically not 100% simplified, because I could add the numerator using a common denominator and simplify this a little more. But I think it's just easier if we take that whole numerator as it is. So 1 over x plus 2 equal to 0. And now we can solve this equation. Okay, so here, how do I solve rational equations? I just multiply both sides by the lowest common denominator, which is just x. Okay, other ways I can solve this, but this is pretty easy. So this just becomes 1 plus 2x equals 0. 2x equals -1. X is equal to -1/2. Okay, so this seems to be the solution to my problem. But like I said, for just to be sure, I should be sticking this back into the denominator, making sure it doesn't make the whole thing equal to 0. So if I have 2 times -1/2, that's just going to be, this is just going to be a -1. But I know that ln of -1/2 is not going to be equal to 1. Okay, so that means this value is not going to make the denominator 0. So it looks like that's my final answer. All right. Any question on this one here? Because a few people asked this one.
I have a question. So the reason why we don't make the denominator 0 is because then it would be undefined.
Exactly. We just don't care about that. Exactly. These, all I want to know is when this derivative is equal to 0, since it's in fraction form, as long as the numerator is 0 and it doesn't make the denominator 0. So that's why I did the little check. I was pretty sure that wasn't going to happen, but it is good to check. If it makes the numerator 0, but not the denominator 0, then you've solved the problem. So good?
Okay. Thank you so much.
Okay, great. So I got one more that came in by email. So of course you folks are more than welcome to stick around. So it's number 8 on page 575. So let me see if I can just do it on the other side. Yeah, it's not too bad. So here, page 575, number 8. And let's take a look at what this says. It says, determine the equation of the tangent to a curve defined by that is parallel to this straight line. So very similar to the one we solved before. So the strategy will be the same. Okay, just we're dealing with different functions. So it's ln x minus 1. And it needs to be parallel to 3x minus 6y minus 1. And as you've all seen, the textbook loves standard form. So this is going to be similar to before. It has to be parallel to this line. So in other words, it has to have the same slope. So I'm just going to rearrange this. So 6y is equal to 3x minus 1. So y is going to be equal to 1/2 x minus, well, I actually don't care about that other part, but I also find it. So I know that the slope of the tangent that I'm looking for is going to be equal to 1/2. Okay, so let's start by taking the derivative. Derivative of ln x is just 1 over x. Derivative of -1 is just 0. So now I just have to make this equal to 1/2. And I don't even need to solve that. I can see straight away that x needs to be equal to 2. And so now I can input that into my function to find the y value, ln of 2 minus 1. And yet again, I've got this, annoying number, but because I'm going to work with slope-intercept form, it'll be not slope-intercept form, point slope form. By the way, if somebody wants me to solve y equals mx plus b, just let me know. I will do it. But I'll just now use y minus the y value, ln 2 minus 1 equals the slope 1/2 times x minus the x value 2. And I'm just going to isolate the y. So it's going to be 1/2 times x minus 2 plus ln 2 minus 1. Okay. Does anybody want me to do slope-intercept form, or are we good with this? Okay. So I'll do 7a in a second. I'm just going to answer a question that came in that says, general question, what kind of communication concepts will we have to be wary of? Do we need to know concepts like how to solve the derivative of sine via algebra. So I would not expect to be having to determine any derivatives using the limit definition or, even what we did yesterday on using the chain rule to find the derivative of logarithmic functions. Okay, but you need to know all the derivatives. You need to understand, what a derivative represents, that it represents a rate of change. You need to be able to, find tangents, solve problems regarding tangents. Don't forget, there's a couple of those special limits that we saw could help us solve other limits, so there's, questions like that. You need to be able to understand that new way of using exponential, exponential models. So it's hard to say. Obviously, I'm not going to tell you what's on the test, but a communication question could be related to any one of these things that we would have done. But no, I wouldn't expect to give something where you're using the limit definition to determine a derivative. Okay. Does that answer the question? Okay. So here, somebody asked for 575 7a. So here it says determine the equation of the tangent to the curve at that point. So again, another tangent question. So let's do it here. Page 575 7a. Okay, so let me just write the function down. So ln of the cube root of x. Okay, ln of the cube root of x and divided by x. And we are looking for the equation of tangent at, what is it? X equals 1. Okay, so again, I'm going to follow the exact same pattern as I did before. Okay, I need to find a point. I need to find a slope. So here it's a little different because I don't have the slope. I needed to find the x value. Here I have the x value. So right away, I can determine the y value. Might as well do that now. So ln of the cube root of 1 all over 1. And of course, the cube root of 1 is just 1, and ln of 1 is just 0. So there we go. It's 0. So the point we're working with is 1, 0. All right. So now let's find the derivative function so we can determine the slope of the tangent at 1. So here I'm going to have to use the quotient rule. Okay. And of course, in taking the derivative of this top part, I'm going to have to use the chain rule. Okay. So let's start with the derivative of the numerator. So here, this is my u. What's the derivative of ln u? Is 1 over u, whatever that is. In this case here, it's the cube root of x. Okay. And now I have to multiply that by the derivative of u with respect to x. So this is like x to the 1/3. So this is going to be 1/3 x to the negative 2/3. All right. And then multiply that by the denominator function. Okay. Then subtract the numerator function. Okay. I'm running out of room. Okay. Times the denominator of the derivative of the denominator function, which is just 1. And then all of that over x squared. Okay, now this thing looks awful, but the good news is I'm evaluating at x equals 1. So there's like no way I'm going to waste my time simplifying this, because inputting x equals 1 is going to be pretty easy. 1 over cube root of 1, that's just 1 times, okay, this 1/3. This is 1 over x to the negative x to the 2/3. But of course, x to the 2/3, it's just 1. That's still going to be 1. Okay, here, another x. There you go. That's 1. And then minus. We did this one already. ln of the cube root of 1. ln of 1 is 0. So this whole thing is 0 all over 1. So in the end, despite the fact that it looked pretty ugly, it turned out to be a fairly easy derivative. I'm just left with 1/3. Okay. So if you have to input a really easy number, not worth simplifying. All right. And so now I've got the information that I need. So I have y minus the y value, which is 0. is equal to the slope, 1/3 times x minus the x value. And there you go. There's my line in point slope form. So again, just you see how easy point slope form is. You don't have to do any work of solving. Okay. Any other questions we want to ask? No. Okay. So I'm going to stop the recording now.